A lot of people, I do these recordings, and I know not many people watch these, but I do this for people who miss the class because, you know, every day I get asked, even this morning, 5 people asked me, what's going to be on tomorrow's retest? What numbers are going to be on there? And so it's like, after a while, it gets, kind of tiring saying the same, thing over and over. Nomenclature number 38, nomenclature number 38. And so I do these videos here in case you miss it. If you miss it, then you can catch it on the video. So this was chapter 2, and so you could go back and take a look. It's a natural abundance problem from chapter 2. Go back and look. I probably had repeated it about 5 times because this error happens every semester, but just this semester was much more significant as far as the numbers that made the very common error. And it go back to that whole thing about abundances and that kind of thing. And if you check out the video, I probably said it about 5 times about the most common or one of the most common errors with those. But since about 90% of the class made that error, then maybe it didn't stick, and so you could find out. But just make sure the units cancel. If on this retest, if you just don't even have any units, and lots of people don't like units for some reason or other, and if you don't have any units, a lot of people don't have any units and they seem to get the right answer. I mean, even if you make this error, you kind of get the right answer because the precision of the calculation isn't so high. It's kind of qualitative because of the certain factors in it. But anyway, that's the biggest hint I'm going to give you.
This isn't really. It's less. It's about the question still, but I'm not really asking for answers. But it's just because the wording on it was a little bit weird when it came to the X in the tutorial. I don't know. What was that asking for or about? What was with the X equals 16, 17, or 18?
That means you could have any oxygen in there. This was there are 4 points I was looking for in that problem. One of them was that when you have 16, 17, and 18, I'll give you this hint, maybe, or maybe not. Do you know what the difference of 16, 17, and 18 was all about? 16, 17, and 18 were the isotopes of oxygen. Yeah. Do you know that each of those weighs a different amount? So what weight should you use? And that's it. That's the only hint I'm going to give you. What weight should you use if you have a mixture of 16, 17, and 18? So that's why I put that in there. 16, 17, and 18, a mix of 16, 17, and 18 is, I don't know, should you use 17 in the middle? Should you use 16? Should you use 18? So it was kind of a complex problem because there are things about different things. But if I specified 16, then you wouldn't use that weight, maybe, or maybe you would. I wanted to see what weight people used, and so the other situation is, and this brings me back to that particular engineering class that I took, because a couple of things that surprised me on the test in that engineering class, and it might have been covered earlier because I petitioned to skip the prereq for that class, so I was supposed to take Intro to Engineering, but I didn't want to sit through Intro to Engineering, so I asked the professor to let me in to the class. He was fine. They don't care there. Usually skipping prereqs is a bit easier because they don't care if you get an F or not. They aren't going to say you're going to get an F, which is good. But let me tell you, let me give you a little hint. So they I told you about that dimensional analysis where they never gave the equation, and a lot of my classmates were saying, "Oh, he never gave the equation. How are we supposed to do this?" And then it turned out it was pretty simple. It was really simple dimensional analysis problem. And then there was another problem he gave. Another problem he gave on the test was missing a key piece of data. Like, okay, how can you solve this? And so some people left it blank. They didn't write anything because it said, oh, we're missing the data. We can't solve it. But that wasn't really the case. The data was missing. So there were two things that the professor was expecting you to do. I did this. I did a range. I picked the smallest number that was reasonable and the biggest number that was reasonable. And I said, okay, it's going to be between this, within this range is the answer. You know, because it's not an infinite number of answers. It's a finite number of answers within that tight range. That was one. Or the other option that the professor was looking for was if you can assume, okay, let's assume this number, which is a reasonable number. Let's assume the density of water is, well, I need the density of water. I need the density of water to solve this to 6 sig figs, right? Well, that's if you want to solve it quantitatively very precisely, right? But you don't have to solve everything super precise. There are other things. So what you can do is what we always do. We assume that water is 1 gram per milliliter, but 1 gram per milliliter is only 1 sig fig. What kind of answer are you going to get? It's not going to be a great answer, but it's better than a blank page. And so this is like, okay, you need the density of water to solve this problem, but the professor didn't give you, so you're going to leave the question blank, you know? And so some people did. Some people left the question blank. It wasn't that easy, but it was along those lines. And so so I did the range. Some other people just assumed the value, you know, and some people just didn't solve the problem because they said the data is missing. You can't solve it. And so you could solve it. You just solve it the best you can. And so the situation in science is you don't always have the perfect answer. You know, if you're a mathematician and you solve some of these problems, you're going, that's wrong. You can't assume the density of water is 1 gram. It's 0.996783, right? But we do it all the time. We do it all the time because it depends on how good of an answer you want and how much time you have. And so oftentimes we just go with what the best data we have. And so I'll tell you, you could have gotten it to 2 sig figs, the answer, with the data that you had. But the other hint is I'm going to give you the mass of a deuterium to 6 sig figs on the 0.2014 something. Just wrote it down. No surprises here. So I just wrote the deuterium mass to 7 sig figs, 7 sig figs. But you should have known it to at least 2 sig figs. You know, it's not going to be 1, it's not going to be 3, it's going to be, you know, and it's going to be close because the mass defect isn't so big. Mass defect is pretty small. But anyway, that's another hint. So you'll need that. Well, just try to figure it out. You know, this X is just the isotope. This is a naturally occurring mixture of oxygen. Here, 16, 17, 4, 18. So naturally occurring oxygen, and we have a lot of it. So what do you do in that case? Well, try to figure it out. Things that might help are going back to this. Somebody asked me, is this the percentage for deuterium? No, that's not the percentage for deuterium. That's percentage for this molecule. whether oxygen is 16, 17, or 18. This is the percentage of this. All right, so that's a preview. Now, we can take a vote. Do you want me to work this problem out for you and give you a different problem? No? Okay. Then maybe you should team up with other people and try to figure it out, see and get it.
There's no way you would like tell us who got it right?
No.
Okay.
I got the same question. No, sorry.
It's one person in this class, right? Not the morning
Okay,
class.
if that person volunteers and is like, I got the right answer.
Multiple people in this class and multiple people in the morning class.
Okay.
Although, did not make this particular common error, which was, I think I know why it was more common this time, and it's because I kind of led you to that. I led you to that because you probably are thinking you need to make very precise and accurate calculations for everything, but not everything's always super precise and accurate. And so that's why I'm giving you this retake opportunity. I didn't even change the order. It's the exact same. All I did was I copied and pasted it there. That was it. All right, any other questions? Just go back to chapter 2 or something, or even chapter 1, but primarily chapter 2, and then try to look, because the transcript is there. I don't know if you could scan the transcript or search the transcript, and then just look for common error or a common mistake or something. All right, I got to continue on with chapter 5 here. One final comment. If you can't figure it out by tomorrow morning, just do what you did before. I'll give you partial credit. If it's just one mistake in a chain and everything else is correct, I'm not going to deduct a huge amount of points. I just didn't assign points on this one because too many people, like I said, made the same mistake. So maybe something, was wrong with it. So
no curve.
What's that?
So no curve.
What do you mean by curve?
Oh, like on the grading scale. Just thinking about it. It's coming from our conclusion.
Well, let me show you the typical curve.
All right.
The typical curve is not bell-shaped.
Oh.
Sometimes. The typical curve is like this. A bimodal distribution, and not even like a symmetric bimodal distribution. You have a few people up here and lots down here. So maybe the question, that was for this particular question. I didn't like the distribution on this particular question. So that's fine. Uh, One final comment on this. You might be discouraged right now, but sometimes it'll come to you. Like your brain is always working to try to find the answer, and this happens. Hopefully, it happens before um, the retest. But this happened to me when there was a question that stumped me on the test. This was at UCLA. I couldn't figure it out, and um, and then finally time was up, and I couldn't answer it. And then I was sitting at Ralph's across the street from UCLA in the checkout line, and then I reached the cashier, and then it hit me just an hour too late, but I got it. Anyway, it might hit you. Hopefully, it hits you before the test tomorrow. So don't give up. Your brain, your subconscious is trying to solve it. Just keep working at it. So we have these as the reactants here. We're just continuing. Is this where we left off last time? Okay, copper is a reactant here. But what I had to do was I had to reverse the equation on the chart. So if I take a look at the chart, I have copper as a product here. But the reactant is copper 2 plus. I don't have any copper 2 plus in my inventory. So what I'm going to do is I'm going to flip this equation so that copper is the reactant and copper 2 and 2 electrons are the product. And so now this is correct. These are called half reactions because a nitrate and 4H plus, they want to take 3 electrons. Actually, it's a nitrate. The H plus is here to stabilize the oxygen. 2 of the oxygens combine with 4 of the hydrogens to make 2 waters. So that stabilizes the oxygen. The other oxygen is left on, nitrogen. And so, do you know the oxidation state here on nitrogen? Oxygen's oxidation state we could give its usual or normal oxidation state because it's more electronegative than nitrogen. So oxygen is normally what? -2. -2 times 3 is -6. -6 plus x is -1. So x must be +5. So we have nitrogen in the +5. It gains 3 electrons. And then it's going to drop it to, what's the oxidation state here? 2. So we're going from +5 to +2 by gaining 3 electrons. So what we call this nitrate, we call it an oxidizer. Oxidizers take electrons. All right, so nitrate and H plus will oxidize something. What are they going to oxidize? Well, they're going to oxidize copper. As copper is going to become oxidized, that is, it's going to lose electrons here to form copper 2 ions. And in this reaction, it goes from 0 to +2, losing 2 electrons. And so we call these half reactions because we don't have a bottle or a jar of electrons. The electrons have to come from something else. And that something else we're specifying here, which is copper. And so this is a half reaction as well because the copper is losing electrons and it's got to lose electrons to something else. And that something else is nitric acid over there, nitrate and H plus. So copper is the reducer. And nitrate and H plus, the oxidizer. Now, I'm going to talk some more about the jargon here. And have you ever heard of oil rig? Oil stands for Oxidation is what? Loss. Loss of what? Loss of electrons. So we look at this. Which one of these is oxidation? Is it the first half reaction or the second half reaction? The second half reaction. So this one is called an oxidation half reaction. And what we say is that copper was oxidized. Copper was oxidized by the oxidizer. But the oxidizer is not oxidized. You know what happens to the oxidizer? It's reduced. So we have RIG. Reduction is gain. And so nitrate and H+, that gives us our reduction half reaction. So we always need oil rig. Oil on the right here, rig on the left. Oil rig. We can't have oil oil or rig rig. Oil oil, you know, nobody's taking those electrons and you can't follow them up. And so it's not going to work. Or rig rig, you know, both species want electrons. It's not going to happen. Somebody has to give up. And so it's got to be oil rig. Always. Okay, so we picked the strongest oxidizer, which was nitrate and H+ in acid. And we picked the strongest reducer present, which is copper, out of the list that we have. The next thing we have to do is we have to add these two up. But there's a mismatch in the number of electrons. There are 3 electrons here. There are 2 electrons here. So if we double the copper, that gives us 4 electrons. It's still a mismatch. So if we double the copper, that's 4 electrons. If we double this, it's 6 electrons. And it's still mismatched. So we'll triple this. In other words, the easiest thing is just to cross multiply. And so I'm going to cross multiply here, multiplying the first reaction by 2. So I'll need 2 nitrates, and that's going to give me 8 H plus 6 electrons, gives me 2 NO and 4 H2O. And then the second reaction I'm going to triple. So that's 3 coppers, gives me 3 copper 2 plus 6 electrons. Now the electrons are balanced. So we have 6 electrons being consumed and 6 electrons being lost. We can't have free electrons left over because those are terribly unstable. All right, next, we're going to combine the 2 half reactions to make the net redox reaction. So I'll just add everything on the left from both equations. 2 nitrates plus 8 H plus 6 electrons plus 3 copper solids. This is going to produce 2 NO gas plus 4 H2O liquid plus 3 copper 2 ions plus 6 electrons. All right, then we simplify. We simplify like we do in net ion equations. We just cancel out the spectators. Although the electrons are not spectators, you know, 6 electrons are consumed, 6 electrons are lost. In the equation, we'll cancel them out. But before I go too far, I need to look and see if there's a driving force, because I don't want to spend a lot of time cleaning up this reaction if there's no driving force. So in order to determine the driving force, we're going to have to label the oxidizer which is nitrate and H+. This is the oxidizer, or oxidizing agent. And then we're going to have to label the reducer, which is the copper. All right, then what we have to do is we have to envision this reaction going backwards. And so what would be the oxidizer and reducer if we went backwards? And so what we're going to do is we're going to take advantage of the conjugate relationship. If we have an oxidizer here, this is a moderately strong oxidizer. If it's a strong oxidizer, then the reducer is going to be fairly weak. its conjugate. There's a seesaw relationship here. So NO and H2O is the conjugate reducer of nitric acid. So NO and H2O, this is our reducer, or reducing agent. Copper, that's supposed to read reducing agent. So if copper is our reducing agent here, then that means our conjugate oxidizing agent is not the electrons. The conjugate oxidizing agent is this, copper 2. Then pick one. All you need to do is either the oxidizers or the reducers, whichever is easier. In this case, let's just look at the oxidizers. So we're comparing nitrate and acid versus copper 2. We ignore the coefficients. It just tells us the right stoichiometric ratio. So I'll try to find nitrate in acid versus copper 2. Which one's stronger? Nitrate in acid or copper 2? Nitrate in acid. So we have driving force here. The driving force is going from stronger oxidizer to weaker oxidizer. Because of the conjugate relationship, the reducers will be the same. It'll be stronger reducer to weaker reducer. We can verify that as well. In fact, let's verify that now. If I was in a rush, I'd only do one. If I have time, I'd probably do both. Need some more pages here. So we have nitrate and acid here, and that's reacting with copper metal. These are our two reactants here. So I could use the zigzag method here. Come on, this would be my zig. So nitric acid attacks copper. What forms? That's not completely wrong. Copper 2 ions. So copper 2 ions, oops, I didn't want that. Copper 2 ions, well, that's simple. That's going from a stronger oxidizer to a weaker oxidizer. That's down here. And the zag part comes here as well. So we have two zag parts. And so we're going from copper to NO. If we go from copper to NO, is that uphill or is that downhill? It looks uphill, but it's downhill. This is a stronger oxidizer to weaker oxidizer, because on the right side of the chart, we live in an upside down world. And so that's it. And so we have our driving force. Oops. Stronger to weaker and stronger to weaker. Because of the conjugate relationship, it always has to be the case. Strong, strong to weak, weak, or weak, weak to strong, strong, because the zag part is going to mirror the zig part. It's just inverted. All right, since we have driving force, let's go ahead and rewrite this and just clean it up here. So I have my two nitrates, 8H plus 3 Cu solid goes to 2 NO gas plus 4, actually was it 4 H2O, did I get that right? Yeah. 4 H2O liquid plus 3 Cu2 plus. So this would be the final. When we check our equations, obviously if we could check the solution in the manual, that would be nice. But what do you do if there's no solution in the manual? Well, you do things like make sure the units cancel, double check your calculator input. Well, here we have no units. Here we don't punch in the calculator. So what we do with equations like this is we make sure the atoms are balanced. So I have two nitrogens, 6 oxygens, 4 oxygens plus 2 oxygens give me 6 oxygens. 8 hydrogens, 4 times 2 is 8 hydrogens, 3 coppers, 3 coppers. So the atoms are balanced. Then we check if the charges are balanced. So over here I have 2 negative charges, minus 2, 8 positive charges. So minus 2 plus 8 is plus 6. This is neutral. Over here, 0, 0, 3 times 2 is plus 6. So plus 6 on the left, plus 6 on the right. So this is balanced. So at least I know it's balanced. I might have screwed up with the driving force or something else, but at least I've got this far. So, this is partial credit for sure if something else is wrong. But this is the correct answer here. Sometimes consecutive reactions occur. And so let's take a look at some of the observations that we would expect for this. Do you know the color of nitric acid? It's called the CCS, if it's fresh. CCS. CCS stands for? Yeah. And then what color is copper metal? Brown? Okay, we'll call it brown, solid. Do you know what color this is? This is called nitric oxide or nitrogen monoxide. Most people call it nitric oxide because nitrogen monoxide is kind of cumbersome. So nitric oxide's a bit easier. And we use the Ich-Aus. Are you guys familiar with the Ich-Aus convention? NO, this is nitric Ich oxide. We have nitrous or nitrous oxide. Have you heard of nitrous oxide? Yeah. The formula for nitrous oxide is N2O. And so when we look at nitric oxide, nitrogen is +2. When we look at nitrous oxide, nitrogen is +1. So the Ich refers to the higher charge. And the Aus refers to the lower charge. +1. But is +2 the highest charge on nitrogen? No. We have +3 nitrogen. So what would you call +3 nitrogen? I'd probably call it per nitric acid, maybe, or per nitric oxide. What do you think? Hyper? Per nitric oxide? But +3, is that the highest? No, because there's something even higher. What's higher? +4 nitrogen. +4 nitrogen exists. What should we call +4 nitrogen? Maybe per nitric oxide? Yeah. And then the highest charge on nitrogen is +5. And maybe we need to come up with new names for this, right? And so that's a major failing. There are just two, and so we start running out. No, if you have +4 nitrogen, it's NO2. We call it nitrogen dioxide. Oh yeah. The higher ones would be N2O3, NO2, N2O5.
So you would just be forced to call them by their formula name? Or like
Which is a bit cumbersome. This would be called dinitrogen trioxide. Or other people do nitrogen Roman numeral 3 oxide. This one would be called nitrogen dioxide or nitrogen Roman numeral 4 oxide. They use the ionic nomenclature for that. And then this one would be dinitrogen pentoxide, which would be nitrogen Roman numeral 5 oxide. There's a lot of different names associated with this, but we're not going to learn all the names. Oops. So if we look at the AI overview here, nitrogen oxide refers to the chemical compound dinitrogen pentoxide, which is also called nitric anhydride. Well, there you go. They call it nitric anhydride. But do you want to memorize all the variations of the common names? It's too much.
what's a solid?
I don't know what this melting point is.
It seems like it was very near the temperature.
Yeah.
What is that? Supplies?
Yeah, we need to know its melting point. Wow, this paper was published in, what was this, 1950? No. Oh, 1840. Probably the oldest paper I got a copy of was one from 1890 something. It's published in the American Chemical Society, Journal of American Chemical Society, which started in the 1800s. Yeah, it's amazing.
how old does a paper have to get before you can't really cite it anymore, respectively? Besides, like,
No, the people are citing papers old. When I was applying to graduate school, they a lot of schools required a reading knowledge of German because they wanted you to search some very old German papers that were like from the 1700s and
what was
stuff
Principia
like
written
that. What's that?
in? What was Principia written in?
English, I think. Yeah. But a lot of chemistry was in German in the turn of the century, the turn of the 20th century.
Makes sense. A lot of the names you see that's
Yeah, yeah. But I ended up going to UCSB, which didn't have what we had to do was we had to get a paper and then translate it using a ink dictionary. So it wasn't hard. It wasn't hard. That was a language requirement. Now the language requirement's gone. Everything's in English. And then when I was at UCB, I had to get some Russian papers, some French papers, then they were written in Russian and French and stuff. But there was this guy there who translation was his hobby. He worked in the stockroom, but he translated all the papers, and then he did a really great job translating. So I just gave him the papers, and he translated all of them. It was very nice. Well, nowadays we're lucky because everything's in English, you know.
It's like the SIU of language.
Mm-hmm. Nice. So nitric oxide, NO, is actually a CCG. What does the CCG? Clear colorless gas. Water is a CCl unless there's stuff inside the water. Like, for example, copper 2. If there's copper 2, do you know what color the water turns? Blue. You might have seen it, or it might have been too faint to see, yesterday, but it should be blue. So let's take a look at this reaction here. This is just copper and nitric acid. This Royal Society of Chemistry has nice videos and nice lectures. This video wasn't the best, though. There are better videos showing the reaction of copper with nitric acid, but we'll just watch this.
In Key Stage 3 and 4, students perform experiments that chemical series.
There's some copper, looks like copper turnings at the bottom of the test tube here.
So when it gets to A level, it makes sense to show students that copper will actually react with some acids. In fact, its reaction with nitric acid can be particularly impressive, as we'll see here. There's more to an acid than a bunch of dissolved protons, after all. So this experiment is a twist on a classic. You'll need 5 grams of copper turnings, and 40 milliliters of concentrated nitric acid, and a 1 litre borosilicate flask. Round bottoms is preferable, as you can see the reaction better, but if you need to get a thick-walled borosilicate flask, a Buchner flask may be a suitable alternative. Immediately we begin to form NO2 gas above the copper nitrate that's formed. Flask. Round bottoms is preferable, as you can see the reaction better, but if you need to get a thick-walled borosilicate flask, a Buchner flask may be a suitable alternative. Immediately we begin to form NO2 gas above the copper nitrate that's formed. I've got a delivery tube here that's feeding into a 1 litre flask of water. The glass wall is there to minimise diffusion of any of the toxic NO2 that doesn't dissolve, and as such you can perform this experiment without the use of a fume cupboard. As the reaction cools, the gases inside the flask will contract, drawing some water back from the conical flask. This is where additional steps have been taken to minimise risk. There's a small chance that the reaction flask could be damaged by the rapidly changing temperatures which follow the addition of the water. As such, if this experiment is performed in the open lab, both students and the demonstrator should be protected by safety screens. A trough or bowl is placed underneath to contain the mixture in case of any leaks. I've placed a small LED light in mine to help the camera pick up the colours.
So what happens is this: there's no brown gas. Do you see? Nitric oxide is a colorless gas. And so where did that brown gas come from? The brown gas came from the reaction of nitric oxide gas with air. And this forms nitrogen dioxide gas. Let me balance this. This is the brown gas. Nitrogen dioxide. Then they're trying to scrub the gas. And so that brown gas, they're feeding into water. And they're converting that into you know what they're converting this into? Nitric acid. Nitric acid, aqueous, consists of H plus and NO3 minus. So what's happening in this reaction here? This is the scrubber. So this is an example of a skeleton redox reaction. It's redox because we see a change in oxidation state. What's the oxidation state of nitrogen in NO2? +4. What's the oxidation state of nitrogen in HNO3 or nitrate? +5. So this is a redox. And how do you identify skeleton redox? The major product is going to be given in a skeleton redox. No. The amounts, we'll have to balance it. And so let me talk about skeleton redox now. The method involves separating the skeleton redox into skeleton half reactions. So the first half reaction we have is NO2 goes to nitrate. And so let's analyze this one. In skeleton redox, what we do is we balance all elements other than oxygen and hydrogen first. And so that leaves nitrogen. We have one nitrogen here on the left and one nitrogen on the right. So it's already balanced. We don't have to do anything. If it wasn't balanced, we'll change the coefficient on one side or the other. After we balance the nitrogen and any other atoms or elements that are not oxygen or hydrogen, then we balance the oxygens. I have 2 oxygens on the left and 3 oxygens on the right. So the oxygens are not balanced. But the way we balance them is kind of funny. Do you recall how we balance oxygens in skeleton redox? We don't add O. I'd like to add one O over here. We're not going to add O. Instead, we're going to add not O, but H2O. So for every oxygen that I need, I'll add one H2O. Because I only need one oxygen, so I'll just add one H2O. That's going to give me one oxygen from here and two oxygens from here, so that gives me a total of three oxygens. So now it's balanced. Check that off. Do you know what element I balanced next? What's that? Nitrogen actually was balanced first. Hydrogen. So I have two hydrogens on the left, but I have no hydrogens on the right. Do you know how I get those to balance? I add H+. So I'm going to add two H+ to the right, and that will balance out the hydrogens. And then finally, I balance the charge. And so what I do is I sum up the charge on the left and right. So NO2 is neutral, H2O is neutral, so I have zero charge on the left, and then NO3 has a negative charge, and then I have two H pluses. So -1 plus 2 gives me +1. And the way I balance it is by adding negative electrons, that is, negatively charged electrons. And so I'll need to add one electron. And so I have a +1, -1, that gives me 0. And so 0 and 0. It doesn't have to balance out to 0. All right, so that was the final step. And then I'm going to add everything up on the left and everything on the right. And so I have NO2 plus H2O yields NO3 minus plus 2H plus an electron. Is this my oil or rig? The reaction at the bottom. Is that an oil or is that a rig? That's the rig? Is that oil? It's rig? Rig? We need some consensus. Oil? Anybody else for oil? How about rig? Huh? You're in, okay. There's only, it's a 1-to-1. You'll go rig too. Anybody else?
I got it. I'm sure you got it.
Well, rig stands for what? Reduction is gain. And oil stands for is loss. So are the reactants losing electrons or are they gaining electrons going left to right? They're gaining electrons? So, well, actually, let's think about this here. What's the oxidation state of nitrogen in NO2? +4. What's the oxidation state of nitrogen in NO3 minus? +5. So to go from +4 to +5, do we gain electron or do we lose electron? We lose. Yeah. So here it is. Yeah. So yeah, this is oil. And so we call this the oxidation half reaction.
Half reaction?
Yeah. It's half because this electron is hanging here. This electron can't be hanging here. We can't have electrons by themselves. It's like small children or something like that. You can't do that. They always have to be accompanied by something. So that electron has to go somewhere. Yeah, so this is the oxidation half. What do we need? We need a reduction half. And the reduction half, so something oxidized this. And so we got to figure out what the oxidizer was. And so what else do we have present in this mixture? It looks like I have H2O present in this mixture. And so maybe it's the H2O. H2O goes to question mark, because we don't know what it is. But we don't have to worry. When we have hydrogen and oxygen, they balance themselves in the skeleton redox method. So let's see how it would balance here. Oxygen would be balanced first. So we have one oxygen on the left and no oxygens on the right. So what do? We add a H2O. Then we balance out the hydrogens. I have 2 hydrogens on the left and 2 hydrogens on the right. And then we balance out the charge. I have 0 charge on the left and 0 charge on the right. Does that look like a reaction to you? It's like H2O goes to H2O. So nothing changed. Nothing happened.
I have permission to use the answer.
Yeah.
You don't get to give me permission, he does. We can't we have just electrons? Cathode ray? Question mark?
Can you take a bottle or jar and capture the cathode rays? If you could capture the cathode rays into a jar and then seal it, and then we could go to the chemical supply company and buy it, then you can have free electrons. Then we'll just pour electrons as needed or take them as required. And so the problem is no, if you had free electrons, it would create such a huge voltage. Even a small number of electrons, let's say you walk across a carpet with like rubber shoes or something, you generate some static electricity. That's not that many electrons.
So when you have something like a cathode ray, that's considered particles?
Cathode ray is a beam of electrons, yeah. But, okay, we could have that beam of electrons, but eventually the problem is where does that beam of electrons end up? So the problem is that the beam of electrons, you know where they end up? They end up going into the cathode. When they go into the cathode, they either go into an electrical power supply and then are pulled into that, or they go into a battery. And the battery, inside the battery, there'd be an oxidizer attached to the cathode, and the oxidizer is going to eat up the electrons. Because electrons go through the air, they hit the cathode, they go through the wire, and then the oxidizers, like these creatures that are just going to gobble up the electrons. That's it. But if we didn't have to have an oxidizer there, if we could have just a jar there, then we would be okay. So the general rule here is if you end up with free electrons in your equation, and your equation is not a half reaction, then you did something wrong. Half reactions are called half reactions because of the electrons here. Can't have them. Well, maybe I made a mistake here. Maybe what else do we have as an oxidizer? We have NO2 and water. What else was present? Is there anything else in water that would be a decent oxidizer? Can you think of anything? Maybe it's got to be O2. Maybe some O2 gets in there to oxidize it. So O2 is going to go to something blank. And I'm just going to leave it blank there because the method should be able to tell us what it's going to form. And so we balance all elements other than oxygen and hydrogen. There are no other elements. Then we go on to oxygen. 2 oxygens on the left, 0 oxygens on the right. And so we'll add 2 waters. Then we'll balance out the hydrogens. I have no hydrogens on the left, 4 hydrogens on the right. So I'll add plus 4 H pluses to the left. Then I balance out the charge. 0 for O2 plus 4 gives me plus 4 here, and then the H2Os are 0. And so I'm going to need plus 4 electrons to balance that out. And so the half reaction should look like this. Oxygen plus 4H plus 4 electrons yields 2 H2O. H2O is a liquid. Oxygen is a gas. So this could be the other half reaction. And when we look at this half reaction, we'll check its balance. 2 oxygens, 4 hydrogens, 4 hydrogens, and then look at the net charge. 0 plus 4 minus 4 is 0. And this is 2 times 0 is 0. And so it's balanced. This would be our rig or oil. This is our rig. And so we need oil rig. Otherwise it doesn't work. And we call this the reduction half reaction. This reduction half reaction might look familiar because if we go back to the chart, you see it here? This is just what we generated. Oxygen plus 4H plus 4 electrons yields 2 H2O. And it's a pretty decent oxidizer. But the other half reaction is off a little bit. We have nitric acid, and so if I look at nitric acid here, it goes to, or not nitric acid, we don't have, I should say we have nitrogen monoxide. We have nitrogen monoxide or nitric oxide here. NO. But when I look at this particular reaction, it's not NO that I'm looking for, it's NO2. So I have nitric acid here. Nitric acid plus 4 electrons here. 4 nitrates plus 8 plus 4 electrons is 4 NO2. So this half reaction, if I reverse it, is very similar to this half reaction. Except rather than NO reacting with water, I have NO2 reacting with water, let's say. And so NO2 and water, it gives me nitrate, 4H pluses, and a different number of electrons, 4 electrons. But here, I have to take a look. There are certain things I can do as far as ranking goes. So both of these are the same, but the difference is between NO and NO2. What do you think is going to be a stronger reducer, NO or NO2? NO2 is not on this chart. And what do reducers do? The rig. Or is it the rig? Or is it the oil? Reducers do what? So if I have a reducer over here on the right side, what do I do going right to left here? Do I lose electrons or do I gain electrons? So I have to reverse this. So let's make NO a reactant. So I'll just flip this reaction backwards. What does NO do? Going to product. And so this is my reactant. These are my product. So NO going to product, does it gain electrons or does it lose electrons? It loses electrons. So my reducers are oxidized. So this is oil. And so if I think about NO, which one is harder to take electrons from? Nitrogen plus 2 or nitrogen plus 4? Which one would be harder to take or remove electrons from? Nitrogen plus 2 or nitrogen plus 4? 2 would be harder or 4 would be harder? Um, how about this? What would be harder to take electrons from? Nitrogen minus 3 or nitrogen plus 5? Plus 5 would be harder to take electrons? Okay, plus 5 will be harder to take electrons from. In fact, plus 5 would be near impossible because it takes too much energy because we would be trying to remove a core electron. That would give us nitrogen plus 6. So you're right. So nitrogen, what about nitrogen minus 3 versus nitrogen plus 4? Plus 4 is going to be harder. And so what we say is nitrogen minus 3, this is electron rich. And so that'll be easier to remove electrons than nitrogen plus 5, which we say is electron poor. Electron poor species are harder to take electrons from. In terms of energy, it's about double. So do you guys remember ionization energy? Ionization energy is the amount of energy required to strip an electron off. And so the first ionization energy, let's say, costs you anywhere from 500 to a couple of thousand kilojoules per mole. And so we get plus 1. The second ionization energy, to go from plus 1 to plus 2, is going to cost you about double the first ionization energy. It gets increasingly difficult. And so going from plus 2 to plus 3 is going to be about another doubling in terms of ionization energy. And so the ionization energy successively increase. The higher the positive charge, the more difficult it is to remove an electron. And so what's a better reducer? The better reducer is the species that's easier to remove an electron from. And so if we're comparing NO versus NO2, that's looking at plus 2 versus plus 4. Which one do you think is going to be easier? Going from plus 2 to plus 3 or plus 4 to plus 5? Plus 2 to plus 3 will be easier. So this is going to be a more powerful reducer. NO2 is going to be up here somewhere. Well, the reason I'm bringing this up is because we need to combine these and we need to find the driving force. And so before I combine them, I'm going to look at the conjugate relationship. So NO2 and H2O, is that a reducer or an oxidizer? It's a reducer. And that means nitrate and H plus must be its conjugate oxidizer. So two ways to tell. One, reducers lose electrons. And so NO2 and H2O will be losing electrons. Two, oxidizers gain electrons. So if we look at these as being reactant now going backwards, it's taking an electron here. So that's the conjugate relationship. And then over here, O2 and H plus, that's going to be my oxidizer or reducer? Oxidizer. Oxidizers take electrons. And H2O liquid will be my reducer. All right, now I'm going to combine these two equations. But I need to make sure the electrons cancel. To make sure the electrons cancel, I'm going to cross multiply. So I'm going to multiply this one by 4. And this one by 1. And so I have 4 electrons lost, 4 electrons gained. Now I'm going to combine these two to make the net redox reaction. So I'll take the oxidation half reaction and combine it with the reduction half reaction. Four NO2 plus 4 H2O. This is gas, this is liquid. Plus O2 plus 4H plus 4 electrons. Plus O2 plus 4H plus 4 electrons. Okay, that's everything on the reactant side. Let's combine it with everything on the product side. 4 nitrate, 8H plus 4 electrons. 4 nitrate, 8H plus 4 electrons. 2 waters. All right, now I'm going to look for a driving force. The driving force will be, okay, going from stronger reducer, stronger oxidizer to weaker reducer, weaker oxidizer. So this is my oxidizer, or this is my oxidizer reverse, this is my reducer reverse. So what's a better oxidizing agent, oxygen or nitric acid? And so we take a look at the oxidizing chart here. We have oxygen here, but this is the wrong oxygen. This is not the strongest oxygen because it produces hydrogen peroxide. This oxygen up here is stronger because it produces more stable product, water. So we're comparing oxygen in acid versus nitric acid. But the comparison is not fair here because the nitric acid does not produce NO. The nitric acid produces NO2. Since we're making a more stable product, it's harder to oxidize. It's going to bump up this. So we don't know how much it bumps it up. And it's hard to determine. So we need more information to determine the driving force for this particular reaction. Likewise, we can compare the reducing agents, NO2 versus water. That's a hard one too. But the 4 electrons do cancel. And we'll leave the driving force as a question mark here. This is one potential reaction. Maybe there's others as well. Depending on what else is present. So that's an example of skeleton redox. If I'm correct, that nitric acid is a major product of this, then we know there must be a driving force. If nitric acid is produced, then we could label this. If there's a driving force, then even though NO2 is not on the chart, I know this is stronger. So this would be a stronger reducing agent versus water. This would be a weaker reducing agent. That means oxygen H plus is a stronger oxidizer compared to nitrate and acid. This one was kind of difficult because of the oxidizer. Oxygen wasn't specified, okay. So I just put it in. All right. So why did single replacement fail? Single replacement predicted no reaction, but we ended up getting a reaction here. And the reason single replacement failed is because of this. Single replacement has the form A plus BX yields AX plus B. So AX in this case is going to be copper 2 nitrate, and B will be hydrogen. But hydrogen likes to be diatomic, so we'll just do hydrogen gas here. The pattern is this. A in single replacement is the reducing agent. B is the oxidizing agent. X is the spectator. So let's say you have a team, sports team or something like that, or a play, and you're the coach or the director of the team or the play. Let's say you're the director and you say, okay, copper, you're going to be the reducing agent, right? And then you say, okay, H plus, you're going to be the oxidizing agent. And nitrate, X, you're going to be the spectator because nothing happens in nitrate. Nitrate stays nitrate. Do you see that? And so nitrate, you're a spectator. But, you know, you're trying to control these, but you can't control them. You're telling nitrate to be the spectator, and you're telling H plus to be the oxidizer. So H plus, you're the oxidizer. Nitrate, you're the spectator. Is there a problem with this? H plus, you're the oxidizer. Nitrate, you're the spectator. What's the problem with this? Do you see the problem? Yes? No? Would be like the out of control kids. You can't control them no matter what you say. They're just going to do what they're going to do, right? And if they're going to do what they're going to do, then what do you think nitrate's going to do? You think nitrate's just going to sit around and do nothing? Even if you tell it to do nothing? You could tell nitrate not to react, but what's going to happen is it's going to react. And when it reacts, when we have nitrate and acid, it's going to be much more powerful than H plus. So this pattern's destined to fail. Because we're telling nitrate not to react, and so no matter how much we yell at nitrate not to react, it's going to react. And when it reacts, it's going to react much more powerfully than just H plus or B alone. So you can't force nitrate to be a spectator, no matter how much you want it to be a spectator. It's not. And so this is a common failure. Nitrate will not be a spectator in the presence of H plus. It turns out that this was misassigned. Oh, it's okay, copper is a reducing agent, but this is terribly misassigned. Nitrate should have been the oxidizer, and H plus could help it. So we have two types of acids. We have acids like HCl. Chloride is happy spectating. You know, chloride's very stable, like fluoride. It's happy spectating. So if this were HCl, then no problem. This works perfectly fine because chloride, no problem, spectator, unreactive, sure. Maybe it precipitates, but that's about it. But nitrate, no good. And so HCl is what we call mineral acid. Most acids, only the H plus is the oxidizer. But then we have a number of acids where the anion is more powerful oxidizer than the cation. Those are called oxidizing acids. So oxidizing acids have an anion, X, that's a stronger oxidizer than the cation, H plus, or B in this case. And so it was misassigned. But there are other exceptions I'm not going to talk about right now. Instead, I want you to use the last part of this class to try this problem here. How much time do we have left? 1 minute?
How much is it, the 420 class or the 4 class?
The 420 is
The lab?
yeah.
Okay.
Yeah, okay. I mistimed this. This will be a reaction we'll look at tomorrow.
Professor?
Mm-hmm.
Oh yeah, I'm not gonna do that for the